Let a of x be the integral from 0 to x of f of t dt with y equals f of x shown. Does A have a local maximum at P? Where does A have the local minimum? Where does A have a local maximum? And true or false? A of x is less than 0 for all x in the interval shown. For part A, does the function a have a local maximum at P? To answer this question, we want to know whether the function a reached its peak at P. We see that this function is known as the area or the net or the signed area so far. It is also known as the cumulative area function. And so, up to this point P, the function a of x is negative because the curve is below the x-axis. And after it crosses P, we would end up with more negative. And so, a does not reach its peak at P. And so the answer is no. A does not have a local maximum at P, even though the function f of x shows that there is a maximum at P. But again, the question does not ask whether f have a local maximum at P, but A, the cumulative area. For B, where does A have the local minimum? A would have a local minimum if it reaches its lowest point or the valley. And we see that if we keep going to the right, then we would end up more negative. This is the sign area until it reaches R. And that is when it turns around and we start adding positive area. And so it looked like A reaches its peak at R. Where do A have a local maximum? We keep adding the positive area to A until we get to S. And so A have a local maximum at S. And then after S, we would end up subtracting the area because the curve f of t is now below the x-axis. And so for part D, true or false, a of x is negative for all of x. This is true because most of these areas are negative. We had a chance to add the positive area, but this area does not even compensate for this large negative area. And so up to the point R, A is negative, but is only added a tiny positive, so A will never be positive. And so this is true. A of x is less than 0 for all of x. There are no coordinates here, so we won't be able to estimate the area under the curve or below the curve. But we can pretend that we can assign certain numbers to these area. Any region below the x-axis has a negative sign. And so if we pretend that this is a negative 1 for now, then this is perhaps negative 2, and this is perhaps positive 0.3 or 0.5, and then this is a negative 0.1. If we were to plot the point x comma a of x with these made up numbers, then when x equals 0, a of x is 0. A of 0 is 0. At the point P, whatever that x is, a is negative 1. When we get to Q, we still end up with a negative, so that would be a negative y value as well, or negative a. When we get to R, again, negative 1 plus negative 2 is now negative 3, and that is at the point R. and then we start adding a positive number, so we turn around until we get to S. And so we have the local minimum at R and the local maximum at S. And then after S, we would need to subtract, and so we would go down, as you can see. There is a better way to answer this question, and that is using what we're about to develop. If we have the sign area so far, or the accumulative function 0 to x at the definite integral of f of t dt, taking the derivative of this will give us f of x. And so taking the derivative of the function a give us back this curve. And by looking at this curve, we can see that f of x is the derivative of a of x. And so using the derivative, we see that at the point P, the derivative is negative and then negative. It doesn't change the sign. So that is why A does not have a local maximum at P. F being derivative, it changes the sign from negative to positive at R. And that is why we have a local minimum at R. It changed from negative, decreasing, and then increasing. And then f is again derivative of a, and f changes its sign at s from positive to negative, and so a is increasing and then decreasing at s, and that is why we have a local maximum at s. And this is called the fundamental theorem of calculus part 1.